Hello students, this is the continuation of the first video, ethers. In this video, we will be learning about the reactions of the ether. And coming to the reactions of the ether, the most important reaction we consider to be the auto-oxidation of ether. Ethers can undergo auto-oxidation to form the hydroperoxide and hydroperoxide that are produced during the auto-oxidation of ethers are highly explosive. So, the laboratory samples of ether must be frequently tested for the presence of hydroperoxide before they are used. And the auto-oxidation of the ether occurs through the free radical mechanism. Coming in details about the auto-oxidation of the ether. So the ether, when they are exposed to the atmospheric oxygen, they undergo the auto-oxidation to give the hydroperoxide and dialkyl peroxide, which are highly explosive. For example, diisopropyl ether, when it is exposed for weeks or months, we'll be getting the auto-oxidized product of the diisopropyl ether, that is the hydroperoxide and diisopropyl peroxide. So, let us learn what is an auto-oxidation. An auto-oxidation is an oxidation reaction that takes place in the open air or in the presence of an oxygen UV radiation to form hydroperoxide and the peroxide and involving the molecular oxygen as the oxidizing agent. The peroxides that are unstable and liable to decompose with explosion or heating. So it is a free radical chain process. This reaction is used for converting the compounds to the oxygenated derivatives. So all the ethers, when they are exposed to the atmosphere to any length of time, contain these peroxides. And these peroxides are highly hazardous because they decompose violently at high temperature. When ether that contains peroxide is distilled, the peroxide concentrate in the residue, and at the end of the distillation, the temperature increases and the residual peroxides may explode. For this reason, the ether should never be evaporated to dryness. So the another example here which I have taken for the oxidation is the auto-oxidation of a diethyl ether to give the corresponding hydroperoxide and diethyl peroxide. Coming to the next reaction of the ether, it is the hydrolysis. So when the steam is passed over the ether under pressure in the presence of dilute sulfuric acid, it results in the formation of the corresponding alcohol, and here in this reaction it involves the breaking up of the COO. For example, when we take your diethyl ether, when it undergoes the hydrolysis in presence of dilute sulfuric acid under pressure, results in the formation of two molecules of ethyl alcohol. So, when I take an unsymmetrical ether like ethyl methyl ether, we get two different types of the alcohol. One is ethyl alcohol and other is methyl alcohol. So upon hydrolysis, we get the corresponding alcohol as the product. Coming to the next reaction, that is the reaction with phosphorus pentachloride. So ether reacts with all PCl5 to form an alkyl chloride. So here this is the general representation of OR plus PCl5 in the hot condition results in the formation of an alkyl chloride plus POCl3. So let us take an example for a diethyl ether. When it reacts with the PCl5 in hot condition, we get the corresponding halide, that is the ethyl chloride. Coming to the next reaction, the action of sulfuric acid. So, the reaction with sulfuric acid can be studied under the cold and in the hot condition. So, let us take in the cold situation. The ether reacts with the cold sulfuric acid or hydrochloric acid, and here we are going to get the corresponding oxonium salts. So, when we take the sulfuric acid, we get the corresponding oxonium salts, and when we take the hydrochloric acid, we get the corresponding chloride, that is dialkyl oxonium chloride. So this is the reaction of an ether in the cold condition. For example, diethyl ether, when it reacts with the sulfuric acid in the cold condition, we get the oxonium salts of diethyl ether. When it reacts with HCl, we will be getting diethyl oxonium chloride as the product. Next, the reaction is with the hot concentrated sulfuric acid. Here there will be a rupture of bond or a breaking up of the bond is occur. So when we take the diethyl ether, we react with the sulfuric acid under the hot condition. Here the products are ethyl alcohol and ethyl hydrogen sulfate. However, when a secondary and a tertiary alkyl ethers and aromatic ethers on this reaction with the hot concentrated sulfuric acid, here we'll be getting the corresponding alkene in the case of a secondary and a tertiary alkyl ether. Coming to the reactions of the ether, which involves the cleavage with AHX. So when an ether undergo a cleavage in presence of AHX, we get a corresponding alcohol and an alkyl halide. So we made to react with we take here the example methyl ethyl ether made to react with the HI. Here we are going to get an alcohol, that is the ethyl alcohol, and a methyl halide. This is an example for the cleavage of ether or unsymmetrical ether. So when a symmetrical ether, we get a molecule of alcohol and the corresponding product, that is the alkyl halide. So we learn in detail about the cleavage of ether by acids. So ether, the substitution reaction with a strong base, that is HX. It can be an I or a PR. So either reacts with HBr or HI in cold condition to form an alcohol and an alkyl halide. So ethers are cleaved by HX to give an alcohol and a haloalkane. This is the general representation. Ether when treated with HX, we get an alkyl halide and an alcohol. Let us take some of the example. Dimethyl ether. A example for a symmetrical ether when it is made to react with HBr and in the higher temperature we get a molecule of an alkyl halide and a molecule of alcohol, and here the products that are obtained are methyl bromide and methyl alcohol. When we take a unsymmetrical ether like methyl isopropyl ether made to react with hydrogen iodide, here we are going to get a methyl iodide and isopropyl alcohol. So whenever we have a mixed ether, halogen attaches to the smaller group, and hence here we are getting the methyl iodide, or that is the alkyl halide. And the order of the reactivity of the halogen is HR followed by HBr followed by the HCl, and the reaction mechanism is SN1 in the is the SN1 in tertiary and secondary, and SN2 in the case of a primary alkyl halide. So let us look in detail about the point of cleavage. If both the alkyl groups are primary or secondary, the smaller alkyl group gets converted into the alkyl halide predominantly. For example, when we take the methyl ethyl ether made to react with HR, we'll be getting methyl iodide and an ethyl alcohol. So the smaller group has been converted to its halide form. So here we are getting the methyl iodide. So if one of the alkyl group is a tertiary, the point of cleavage is such that we always get the tertiary alkyl halide to be the major product. So here when we take a tertiary butyl methyl ether made to react with HR, we are getting methyl alcohol and a tertiary butyl iodide as the major product. So, in presence of excess of HBr, let us look what happens. If two or more equivalent of acids are used, further dehydration can occur on the formed alcohols, which may react further to form a second mole of alkyl halide. So, when diethyl ether is made to react with excess of HBr, as I said, whatever the alcohol that is obtained may further react to give the second molecule of the alkyl halide. So, when we take the aryl alkyl ether, the cleavage occurs in such a way we always get an alcohol and an alkyl halide. So, when we alkyl aryl ether is undergo reaction with an HR, a phenol and an alkyl halide is obtained, and here we are don't get the phenyl halide and an alcohol. So these are the reaction under the cold condition. So when let us look what happens at hot condition. Simple ether as well as mixed ether reacts with concentrated HI to form alkyl iodide. So when the ether, which can be a simple or a mixed, is made to react with the HI in the hot condition, we get the two molecules of alkyl halides. So only alkyl halides are formed in the hot condition. So now let us learn the estimation of ether group by Giesel method. The method was developed by Giesel in 1886 for the estimation of methoxy or ethoxy group in a compound. The methoxy or ethoxy alkane or arene sample is weighed and it is heated with excess of concentrated hydroiodic acid, forming an alcohol and the corresponding iodomethane or iodoethane. So here the first step is either the methoxy or an ethoxy or an arene. We are going to weigh the sample and the weighed sample is made to react with the excess of HI. As a result, we get a molecule of alcohol and a corresponding alkyl halide. So it can be a iodomethane or a iodoethane depending on the whether it is a methoxy or the ethoxy alkane. Coming to the next step, the iodomethane or iodoethane is distilled off and treated with alcoholic AgNO3. As a result, the AgI gets precipitate, so silver iodide gets precipitated, and this is the reaction when it is treated with the AgNO3. So the precipitate of AgI is collected, washed, dried and weighed. So this is the reaction which involves a methoxy, and this is the reaction which involves the ethoxy. So either of the alkyl halide which are obtained in the earlier step is made to react with the alcoholic silver nitrate to get the silver iodide precipitate, which is collected, washed and dried, and the weight of the precipitate is recorded. So now let us look the calculation of the methoxy group. So here we know 1 mole of silver iodide precipitate corresponds to the presence of 1 methoxy group. So the weight of the sample taken is W1 gram and weight of silver halide, that is AgI formed, is W2 grams. So from the above reaction 1 mole of AgI corresponds to 1 mole of methoxy group. So 234 grams of AgI corresponds to 31 gram of methoxy group. So when I want to calculate the percentage of methoxy group, obviously 31 into the weight of the silver iodide into 100 divided by 234, that is the molecular mass of AgI, multiplied by the weight of the sample given, will give us the percentage of the methoxy group. So if I want to know the number of the methoxy group, this formula can be applied where the M is the molecular mass of the sample. So once again I repeat, 1 mole of silver iodide corresponds to 1 mole of the methoxy group. So I calculate the molecular mass of AgI methoxy group. So 234 grams of AgI corresponds to 31 grams of methoxy, and simple calculation we can get the percentage of the methoxy group. So coming to the calculation of the ethoxy group, here the principle is the same. 1 mole of silver iodide precipitate correspond to the presence of one ethoxy group. And as usual, the weight of the sample taken and the weight of the AgI are recorded, which are W1 grams and W2 grams. And we know from the reaction 1 mole of AgI corresponds to 1 mole of ethoxy, and calculating the molecular mass of AgI and methoxy, 234 grams of AgI corresponds to 45 grams of ethoxy group, and the percentage of the ethoxy group is as follows. So these are the steps by which we are going to calculate the ethoxy group. And these are the references for the preparation of this video. Thank you.